Very good afternoon to each and everyone. Myself, Dr. Surat Singh, will be presenting you today various topics that are very important to be studied in digital image processing because until unless you're not creating a data, you're not rectifying the data and you're going to process it, you're going to classify it. So the amount of error that is induced in your satellite image will be carried forward in your output image. So whatever error that was in your input image will be transferred into output image, and finally you will have a error classified maps. So if the classification error is on the purer side, even if you have classified the satellite image, you have identified the objects, the accuracy is poor, so nobody is going to accept the data sets. For getting that data recovered for before processing, you have to rectify all your data sets, like when you are going for driving, prior to going to any if you're planning to go to some neighboring 1500 or 2000 kilometers, what you will do first, you will check the tires whether they have got proper air pressure in it, then you will see the petrol, then you will see the lights, then you will see the brakings. So in the same way, prior to classification of any satellite image, you have to check for each and every kinds of tires and all. In this process, the tires are replaced by various kinds of geometric and radiometric errors that are induced in your satellite image. So why we do this kind of error is produced, and why it is important to correct this error? Because if you are not correcting these errors, if you want to project yourself on the field, you want to project yourself on the ground, you want to see yourself on the world map or Indian map, until unless you don't have a projection system, you cannot identify yourself where you are located. Because for identification, projection is important. Thereafter, if you want to see from here what will be the total distance of Delhi or nearer to Chandigarh or Himachal, so until unless we don't have a projection system, we cannot go for the scaling. And until unless we don't have a scale, we cannot go for the area analysis. And if you are not going for the area analysis, your entire process of classifying a satellite image will be wasted. Because at last we want to see our nature ought to be protected, to be conserved with different kinds of strategies and management procedures. So until unless we don't have the real positioning of that area, another example I will be fitting it, like if you want to bombast your neighboring, there is an attack and you have got a fight with China, and China is saying to us, we are going to fight. So which are the location where we have to hit them? For those locations, the exact positioning or a specific geographical latitude, longitude is required. So geometric errors denotes that the position which does not have a accurate or a nil projection or nil action, right, that is latitude and longitude, are stated as geometrical error. And before classifying any satellite image, you have to rectify this error, and that process of rectification is known as registration, where you will be using the ground control points that are identified on the satellite image. It can be either in two ways. What are the data sets that are available through which you can identify those data sets? Are your satellite images, your survey of India maps, your other data sets. But many times the data sets or the geo-referencing processes or the registered image what you're seeing is only virtual. They are not perfectly geo-referenced to its position. So there are two processes. Either you can rectify it through image to image, or you can rectify it through topo sheet. Through topo sheet, how you will be rectifying it? In the topo sheet, when you will scan up, when you will upload in your system, or whether you download from Survey of India, you will see the digital copy of your Survey of India topographical sheet. But when you want to project it into your system, you want to overlay with the different kinds of satellite images that are available from 1970 to 2020. Until unless they are not having the same projection system, you cannot overlay those operations. And in order to overlay all those images, they must have the same coordinate system, and their source of error should be very less so that they fit to their exact positioning. So, identifying and fitting of the coordinate system from one image system to the another image system with the same area is known as registration. So we can classify geometric errors into two classes broadly. One, error that are caused because of the change in the platform ephemeris, because as the satellite is moving, the earth is also rotating. So many times there is imbalance between the orbit and the satellite. So at that point of time, if any error is generated, that is known as platform ephemeris. And if any error is created because of the defect in the sensor or internal distortion is there in the sensor, that is the other form through which a geometrical error is reduced. And the other one is the exact positioning of the location of the various odd features where they are located. If they are not located within the space where they are supposed to be, then you have to identify the new ground control points that you can easily identify in those satellite images, which are geo-reference, and you can take those features, those lines, those points as a reference for getting your map geo-reference. So they are known as ground control points. So the other important thing and the error that is related to geometrical error is known as skew. Skew is the most common error that is caused because of geometrical distortion, and it's because of earth rotation effect. So already I have said because of the earth rotation, many times the earth observing sun synchronous orbits are normally in a fitted orbit position that collects applause. So always you will be finding that near about they are into a fixed position and they are revolving towards the earth from north to south. And as the satellite makes it way from north to south in the descending mode, so here will be in the ascending mode, here it will be in the descending mode. The earth below rotates on its axis from west to it. So the satellite is going from north to south, and your earth is moving from west to east, making one complete revolution every 24 hours. Every 24 hours it takes to complete one revolution. So this interaction between the fixed orbital part of the remote sensing and the earth rotation on its action is known as skews, and the geometry of the image is collected. So this is called, you can see that how the earth is rotating, how the satellite is rotating, and this is the pixel in the right plane prior to correcting of the earth rotation effect. So without earth rotation effect, you can see that this is a distorted image, but when the pixels of the thematic mapper are corrected for the earth rotation effect, means the earth rotates from west to east, so the entire scan consisting of 16 lines offset to correct the earth rotation effect. So this all data will be dashed line indicates the shape of the distorted image, and solid line indicates the restored image. So the when you are doing skew correction, what will happen? The image will fit to its original location, and the error that was caused was because of the rotation of the satellites and Earth that we'll be doing in our laboratories. Next is, now you have got a error. Now you have to rectify that error. So how you will be rectifying that error? So that the process of geometrically correcting an image so that it is represented on a planar surface conform to images or conform to a map. That is known as rectification. On the other hand, it can be also said as it's a process by which the geometry of image is made polymetric. So it is very important to get an accurate area. If you want to get an accurate area, you want to get a distance, you want to get a direction, you want to have a measurement, because whenever you're creating any kind of map, this all four properties of a map should be protected. And until unless you're not rectifying your image, you're not geo-referencing your image, such properties cannot be preserved. That's why registration is very important. So it is achieved by transforming the data from one grid system to another grid system using geometric transformation. So until unless you are not providing a projection system to your satellite image, it won't fit to its original position. So for that, it will be transformed from an unknown projection system to a known projection system, and the process is known as geometric transformation. In other words, what we can say, it's a process of establishing mathematical relationship between addresses of the pixels of an image with corresponding coordinates of those pixels on another image or map or on the ground. So what on the other hand we can make easily, we can say कि we are mathematically seeing कि what is the amount of error that is induced or that is created when we are creating a new feature that is having the same position of the feature that was on the geo-referenced image, and then we are plotting into an uncorrected or on geo-reference. So the amount of error that is created between the two, that is known as mathematical relationship, and in both the points we are trying to identify the same feature on the georeferenced image, means that is having a projection system, and from that projection system we are trying to provide the unknown satellite image a projection system, and then we'll see mathematically is what is the amount of error that has been created by the user while giving this positioning to that unknown system. So that is known as geometric transformation. So we have already completed what is shift, what is scale, what is rotation, what is skew. So image to image rectification, I have always said that the most popular and the most common process of getting your image rectified is image to image rectification, and in this you can classify the image rectification procedure into two steps. So what are those steps? So two basic properties must be performed to geometrically rectify a remotely sensed image to a map coordinate system. So what are those systems? One is spatial interpolation and other one is intensity interpolation. So we'll be performing two exercises today. One is spatial and the other one is intensity. Now we'll be going into the detail that what you mean by spatial interpolation and what you mean by intensity interpolation. So what do you mean by spatial interpolation? Interpolation is the process where the geometrical relationship between input pixel value or the locations or the rows and columns and the associated map coordinates of the same coordinates are identified. Means what we are trying to do, we are trying to identify the same pixels with the same feature with the image that is having a projection system, and then we'll be assigning the same value to the same pixel, the same feature which doesn't have a projection system. So that identification and that process is known as spatial interpolation. So what does it help? This establishes the nature of geometrical coordinate transformation parameters that is applied to rectify the original image to its proper position in the rectified output image, and involving selecting ground control points and fitting polynomial equation using least square technique. So what we are trying to do, we are trying to identify those features in the image that are very clear, that are seen over the decades, over the year, that haven't changed its position. So those features are generally intersection of roads, intersection of railway lines, then you have got major buildings. Uh, these are the important features that you have to identify, and these features must be, whenever you are identifying, you must be selecting these features from your entire image. Means it must be uniformly distributed throughout the image, because if it is not uniformly distributed, if you are selecting the points from a specific location and you are not taking from the other point, the amount of the accuracy of the map will be very high for the points where you have the maximum number of ground control points, and if you have missed out at somewhere, the amount of accuracy will decrease. So what you have to do in the map, they have got four corners, left, right, then upper left, upper right. So what you have to do, you have to select those points from all the 4 points on the image, so that from all the 4 points or from all the directions, the map fits to its original position, so that when you overlay the different kinds of map together over the decades, there is no kind of error in its position, and that can be done only if you are selecting a good standardized error free ground control points. So the other process was intensity interpolation. So now we know the ground points are known as spatial interpolation. Now we'll be going for intensity interpolation. That is, the pixel value must be determined. So each and every pixel has got a value, that is also known as digital number. So while providing that pixel values, the number, when you're transforming it from one system to another system, what should be my output pixel value in the rectified geo-reference image is known as intensity interpolation. So a pixel in the rectified image often requires a value from the input pixel grid that does not fall neatly on a row or column coordinates. For this reason, resampling mechanism is used to determine the pixel brightness value. So many times what happen, you will be doing a positioning. So what it will do, I'll be just going on changing it. So what I am trying to show is many times there will be a shift. Yeah, you can see then how it is shifted. So such kind of errors are created when you're doing such kinds of transformation, when you're doing it through spatial rectification. So many times it won't fit to its original position. So what we'll be doing, we'll be resampling it, we'll be providing the value. So those values can be on the basis of your nearest neighborhood by linear interpolation or cubic convolution. They are the three resampling techniques through which a pixel identify its value. So that will be reading in detail in our coming slides. So next is spatial interpolation. What do you mean by spatial interpolation? Again, in detail we'll do. So the geometrical relationship uh, between input pixels location and associated map coordinates of the same points are identified. I've already told that you have to identify from both the images the same points with having a projection system that doesn't have a projection system, and that will be done on the basis of ground control points, and that will be using a equation that is known as polynomial equation using least square method technique. So what are ground control points? We are going on discussing about ground control points. So now I would like to have a more in detail about what are ground control points. A ground control points is a location on the surface of the earth. That is the location on the surface of the earth, means on the satellite image or in your topographical sheet, like road intersection, that can be identified on the imagery and that can be easily plotted and can be used as reference to get that other image geo-reference. Just like many times you will be showing that one vehicle is doing touching to the other vehicle, in the same way helping you out to the other vehicle so that it can go to the mechanic for its maintenance. In same way, the satellite image which has got a proper shape and size projection system will be helping the other satellite image to get its positioning done. That is the best simply way you can understanding. So there are two different sets of coordinates associated with ground control points. One is source or image coordinates specified in rows and column, and the other one is reference or map coordinates measured in degree or latitude or meters in universal positioning system. So the paired coordinates, that is I and j, and the projected coordinates x and y for many GCPs can be modeled to derive a geometrical transformation coefficient. So we'll be taking out the coefficient of values of each and every points that we have taken in respect of the positioning what we have stated and what it is a reality in the field. So this coefficient may be used to geometrically rectify the remote sensing data to a standard datum or a map projection. So what can be the common ground control points that has to be utilized for getting your map georeference? So accurate GCPs are essential for accurate rectification. So if you don't have a very good ground control points, whatever output it is coming, if you have got an error free or it has having an error, that is a waste. No, that's of no use. So always try to keep your data, the ground control points, the errors less than a half of a pixel, that is 0.05. That is 0.05 of the total RMS error. It should not be more than that. So we'll be going into detail what is mean by half a pixel of error and what do you mean by 0.05. Okay. So, what I have already stated is the GCP must be well dispersed, must be well distributed throughout the area, must be reliable, must be accurate. Because if it is not reliable, so if you are providing a projection system with the same projection system, the image will be rectified, but the amount of error will be very high. So, what are the features that we generally use those ground control points so that the amount of error is less? That is your road intersection. They are the airport runways, towers, buildings, and for a small scale building, we are using the larger features like urban area or geological features. Landmarks that can vary means the features that are varying, whether that is a lake, water body, or vegetation, should not be used. GCP should be spread throughout the image. Requires minimum number of GCP depending on your transformation. So depending on your transformation, the minimum number of GCP is required. That is, if you have taken a transformation or a polynomial equation one, at least three GCP you have to define. The fourth automatically will be corrected from the system. If you provide two, seven you have to provide, eight it will be automatically generated from the system. So if the terrain is tough, if the terrain is hilly, if the terrain is mountainous, then you have to go for higher order polynomial equation. But if the terrain is smooth flight kind of things and it is a homogeneous in nature, then you can simply use polynomial equation one. You will be selecting three, more or less your purpose will be solved. So spatial interpolation using coordinate transformation, what it says? It says that polynomial equation are used to convert the source file coordinates to rectified map coordinates. So we'll be providing the input value and the output value, and that is transformed on the basis of polynomial equation. And what is that polynomial equation? That depends on the distortion in the imagery, means how much distorted the image is, then the number of GCP used, whether 3, 7, 8, 9, then their location to each other, where they are located, where with respect to each other, and then complex polynomial equations are used. So the degree of complexity of polynomial is expressed as the order of the polynomial. So the more the complex is high, the more is the order. The more there is the order, the more number of ground control points you have to provide to the system, and then the system will be performing the geo-rectification process on the basis of those ground control points. So order is simply the highest exponent used in polynomial. So this is the mathematical transformation, linear transformation or affine transformation, or the first order what transformation what we are talking about. So you'll be seeing that this is the formula that we'll be using for the transformation, that is a0 plus e1x plus a2y plus y equal to b0 plus b1x plus b2y. So where x and y are the rectified ground coordinates, means the output spatial location. So how does that output spatial location is generated from your rectified image? So x and y are the source coordinate input. So x and y, this is small x and this is small y, is those pixels location that was identified from your rectified satellite image. Then x and y is the source coordinate system. Then a first order transformation can change. So if you're providing a first order transformation, what it will change? It will change the location in x and y. Obviously, we want to change. It will change the scale. The scale can be changed. It will change the rotation. It will change the skew. So polynomial transformation, what we have stated is the coefficient. What is the coefficient? It is the coefficient of a0, a1, a2, b0, b1, b2. They are the three coordinates or the three equation or the 3 points what we have used, and they are known. They are known how we have taken those points from the georeference satellite image. The above polynomial can be used to relate the point to its corresponding point in the image and vice versa. In the same way, what it will do, will put this point coordinates to identify the same point coordinates on the other image. So we are trying to create a coefficient in both the images. So 6 coefficients are required for this transformation. So 6, why it is required? 3 for x and 3 for y. 3 for x and 3 for y, means 6 transformation equation is required. That's why minimum 3 GCPs are required for solving it. So 3 point, and we required 3. So you have got 3 x and 3 y. So each and every points will have a coefficient. So minimum how much is required? Minimum 3 is required to get that equation solved. However, before applying rectification on the entire set of the data, it is important to determine how well this 6 coefficient derived from least square regression. So how this polynomial equation is generated? It is generated using least square regression. So we are preparing a regression model, and we are using the method that is known as least square method for initial GCPs account for geometrical distortion in the input image. If you will be creating those polynomial orders, you will be creating the GCP, you will be creating the linear regression will be used, and a final RMS error will be created for each and every point. If the amount of RMS error is very high for a point, even if you have selected as a ground control point from your satellite image, delete that satellite image and try to identify a new ground control point with a lesser amount of total RMS error. So what is the accuracy of this RMS errors? In this method, we can check how good the selected point is fit between the map and the image. Okay, how better it is fitted. So what you have to do? You have to solve linear polynomials. So what we'll do? We'll first take 3 GCPs to compute 6 coefficient, and its source coordinate in the original input image are say x and y and 1. The position of the same point in the reference image is in degree, feet or meters say. So now if the input map x and y are the first GCP backs into linear transformation with all the coefficient in the place, will get the computed or retransformed x and y value, which are supposed to be the value of this point in the impediment. So ideally measured and computed values should be equal. In reality, it doesn't happen. There is always a discrepancy between the measured and computed coordinates, and we have to check for the transformation. So obviously, what we think in your life and what happens is always a two different thing. So in the same way, we are trying to give the best possible coordinate system to that specific point, but many times it differ in the field. So the what is the amount of difference? What is the amount of error that has deviated from its original position is known as root mean square error. Root mean square error. So what does root mean square error does? It identifies the error of each and every point that has taken part in getting the image you referenced. So if the total RMS error of the image is more than 0.5 or a half a pixel of an image, for example, if the spatial resolution is 23.5, if we say half a image, that is 12. So if it is more than 12 meters, error is there in your image, means it will be more than, if you convert that into a figure, into a map, it will be near about 2 kilometers or 3 kilometers, because 1 centimeter on ground equals to 2 kilometer on the surface. So what we are trying to do, we are trying to keep the map error into its own spatial error, means not be deviating from its original positioning. If that will be deviated, what will happen? Instead of, if the there is a navigation in the airplane navigations, their fighter planet that doesn't know that this is road, this is railway lines, they go through navigation. So if you are not checking for the accuracy of the map where they have to drop down, if there will be a difference, instead of going to the runway, they will be putting the air tube to any buildings. Why? Because of slight of error. You said, sir, it was only 2 centimeter on my image, but when I convert this data into the ground, it will be more than 2 kilometers on the surface. So these are known as ground control or root mean square errors. So this method is used to, what is why this method is used? This method is used to involve the data sets. So this method involves computing root mean square error for each of the ground control points. So RMS error is the distance between the input location of a ground control point and the retransformed location for the same ground control point. So RMS error is computed with a Euclidean distance. Okay. So we'll be discussing that in detail in the coming slide. So what does it mean? It is the root mean square error. So how this is created, will be will be calculating all the error that has we have provided that as an input, and the same what it has been retransformed, you can see that, and then we'll be expressing them what is the amount of total deviation that has happened in the field. So RMS error is expressed as distance in the source coordinate system. It is the distance in the pixel width, how much it has deviated from its original location. So an RMS error of 2 means if the total RMS error, if you geo-referenced it at the RMS error is 2, what does it means? That the reference pixel is 2 pixel away from the retransformed pixel. Means if I have got this, I have to go into my neighboring house, but I won't be going to my neighbor to neighbor house. Means there will be a lot of error if the RMS error is 2. So what you have to do, and what is the amount of RMS error that is acceptable, or on which the amount of error will be less and there will won't be many error. So that is depends on the your objective. You cannot say what is the amount or the minimum. That all depends on your objective, what your project says, what the community has decided, or what your boss has decided. So that it's a normally a user defined specifics that allows a certain amount of acceptable total RMS error. So the amount of RMR error is tolerated can be thought as a window which moves around the source coordinate. Whatever we are providing the reference input points or the ground control points, on the basis of that the total RMS error will vary. So inside that we must always try to keep the threshold as less as it can. So that's why I was saying less than a half a pixel, means even if it transform, or even if there is a pixel, it will be transforming within the pixel, it won't be transforming beyond the pixel. Means the position of the object will be near about less, only a fraction of few centimeters can happen, that is 4 to 5 centimeters. So that is acceptable of such 5 to 6 centimeters of error. So you can see this is the acceptable RMS error key if this is the real position, and if your map is coming towards this, then that is more than the error. But if it is beneath the error, matlab beneath the pixel, if the same positional varies, that is acceptable, that can be accepted. So this is the formula that we'll be using for the total RMS error, where Rx represent X RMS error, that is the error related to your longitude positioning, I related to your latitude positioning, then T total RMS error, and number of GCP points you have corrected, I GCP numbers, then XR is the X residuals of the ground control points of I, then Y residuals of ground control points of I. So what is the acceptable RMS error? Again, we'll be saying that is depends on the use of the data sets, depends on the type of data that we are using, depends on the accuracy of the data of the ground control points. So normally the RMS error is less than 1, less than 1. means per GCP, less than 1 per GCP, and a total RMS error of less than half a pixel is acceptable. So always try to keep your RMS error per point less than 1 should be there, and total the cumulative error of all the GCP should be not more than zero point 0.5, means half a pixel. So after computing the acceptable RMS error, each computing of transformation total RMS reveals that the given set of control points exceeds the threshold. Then what you have to do? Then you have to see which point is creating the maximum error when you are providing that ground control point, and you delete that point that is creating the maximum error, and then you try to identify a new point. So you can see that in the current table we can see that how this ground control points are being assigned to the satellite image, and what kind of transformation is being done when you are providing the reference data. So you see that this is the polynomial equation that we have already studied will be taken into consideration for identification of the positioning. So you can see that on the there is a table that states what is the total RMS error. So the RMS error of each point, that is point 1, 2, 3, 4, that have been used, or that are the ground control points, have a error less than 1. So that can be accepted, because if the error is less than 1, means they are more or less beneath the threshold. And then you have got corresponding lat long in the topo sheet and coordinates of the pixels in the satellite image. So what you have to do, you have to identify both those satellite images to get that original satellite image positioning. So what you see here, you can see there is two different kinds of projection system that are existing through topo sheet. If you are going, that is providing in latitude longitude, and if I'm going to the satellite images, you have got a UTM projection. So now we have got three GCPs in satellite images and the topo sheet, thus six coordinate system. So what we have got? We have total got six coordinates, and hence if you have got six coordinates, you have to per coordinate two coefficients. So you have to calculate for 12 values in all. So we'll be calculating the values of each and every points. So out of this, three values of each refers to as x, y, x, y, x1, y1. We'll be using these values to solve the equation, and finally we'll be converting that into the positioning so that they get itself fitted to their real position. So that is known by image positioning. So you can see that how we'll be providing, or we'll be geo-referencing the satellite image. So generally we'll be taking the four corners of the satellite image in order to get it geo-referenced. So other one we have stated. So right now we have completed with spatial interpolation. Now we'll be completing it with intensity interpolation. Okay, what do you mean by intensity interpolation? So here the each and every pixel has a value that is known as digital number. Now we have transformed the pixel, means we have transformed the row and column to its original position. But now what should be my value? What should be my number? What should be my digital number? For that we are calculating and performing this intensity interpolation. So what it does, it decides the pixel value brightness for each and every pixel that has been relocated or readjusted according to its original location. So what it will be showing, will be shown that a pixel in the rectified output image often requires a value from the input pixel image, does not fall neatly on a row and column coordinate. So many times what will happen, the if we are geo-referencing it, if we are trying to put our input image and trying to fit the output image, maybe the values of both the pixels are not the same, there is some kinds of deviation. So what should be the value that has to be inputted, or that has to be entered into the rectified satellite image? So such kind of operation when we are trying to provide, that is known as intensity interpolation. So when this occurs, there must be some mechanism for determining the brightness value to be assigned to the output rectified pixels, and this process is providing a number, the digital number that a satellite has captured when it was sensed by the sensor, and when we are providing a geometric correction to it, the value that will be assigned to my name, my address, is known as intensity interpolation. So what does intensity interpolation do? When an image is wrapped, you have to assign the digital number to the new pixels. In such, the grids of a pixels in the source image rarely matches to the grids for the rear reference image, and the pixels are resampled. That now what you have to do, your pixels will be resampled, relocated, renumbered, so that the new data file values for the output file can be calculated. So what we'll do, we'll be calculating the new value so that that value perfectly fits and it's nearly the same what it was in your earlier image. So this process involves the extraction of the values from the location in the input image and its relocation in the appropriate coordinate location in the rectified output image. So what you have to see, you have to see where this position of the image has gone, where was the original value in the image, and now how the image looked like, and which are the pixels which are nearest to it. So that is this type of resampling are input driven, output driven. So all will depend on the amount of input that you are providing, and that depends on the movement of all the pixels in the image input to their new positions in the output image. So what we are trying to do, post rectification, post classification, not only we are trying to change the position of the satellite image, but many times we'll be changing the values and we'll try to keep the values that are similar to what was there in the input original image prior to any kind of geometric transformation or spatial interpolation. So what are the disadvantages? As you can see that we are trying to move the value of a pixel from one pixel to other pixel. So many times there can be some errors. So what are the errors? Some output pixels are multiple assigned. So maybe we can multiple assign the same value. Like if you're putting a stamp to it, many times you can put a two stamp on a single paper. That is the same way if you're providing a filling the data, it can happen. And some are not assigned, creating gaps in the output image. And many times when you're putting at maybe two pages stuck together and you're going on, and in between the data was lost. So such gaps can also be created in the satellite image. So, as already we have stated that the resampling technique is totally input and output driven. So, what we try to do is we try to identify. You can see that how the positioning is done on a output image. So, creation of a new image is done by filling the pixel after line by line. So, what we'll do first, first we'll identify, we'll fill the pixel value of each and every line, and then we'll go to the next slide. So pixel indices in the output image are transformed to the position of the corresponding pixels in the input image. So this is the resampling technique. So you can see that how the images values are retransformed, relocated on the basis of the given input point. So you see that this is the point before rectification and this is the point post rectification. This is the point post input, this is the point post output. So you can see that how the positioning, how the data, how the value has changed, and it all depends on your input value on the basis of which you will be defining your output value. So how this entire operation is being performed, this process of resampling is the results in the input line and column lines are real numbers, they are not integers. And this method, if when you are doing it, there are the three methods through which you will be assigning the values that to the nearest pixel, that is nearest neighborhood. Then you have got bilinear interpolation, then you have got cubic convolution. So what is this? So from the nearest neighborhood, from the image, you can see that this the nearest neighborhood approaches uses the value of closest input pixels for the output pixel value. So whatever pixel value that is closest to the input image will be assigned as the value in your output image. So the pixel value accompanying the closest image file coordinates to the estimated coordinate will be used for the output pixel value in the geo-referenced image. So in the same way, you can see that this is the corrected image, the dark one is the corrected image, and the dashed line is the original image. So post correction, you can see that the shape has changed. The shape has changed. Now how to identify what should be our value? So we'll be calculating the same row and path in the input image, and we'll try to keep and give the number of that input pixel image to the output image, so that the feature that was supposed to be in the input image, that was the real earth image, doesn't change in the output values. So obviously every techniques has got some advantage and disadvantage. So what are the advantage? The advantage is output values are original output values. There is, because we have not changed any value, we have not created any equation or mathematical transformation, we have not changed. So other methods of resampling tends to average surrounding value. So the other methods what we are going to see, we'll seeing that there is some formula that is adopt, and because of that many times the value change so as the features changes. So this is important consideration when discriminating between vegetation or locating boundaries. Since original data is written, this method is recommended before classification, because all the data are the same that was supposed to be in the original image with the geometrical correction. So I will be very happy with the data sets with all the value fitting to its position, and there is no deviation from its original point. The object which was supposed to be on the ground is supposed to be on the map. So it's easy to compute and fastest to use. It's very easy to compute. You can easily compute and you can fastly calculate it. What are the disadvantages? Each and every person has a disadvantage. Each and every vehicle has got some demerits that depends on perception and time and your experience. It's produces stair shaped effect, and the image has a rough appearance relative to the original unrectified data, because the averaging has not been done and high spatial frequency objects have been written. That's why you will be finding a rough image, because the frequency of change in the object is very high. That's why it will be left. The data value may be lost while other value may be duplicated. The other way of interpolation or is bilinear interpolation. It is bilinear interpolation. So the bilinear interpolation approach uses the weighted average of nearest 4 pixels to get the output value. So whenever we are using the bilinear, we'll be using the 4 pixels to determine the average value of both the pixels will be used to get the value of the new pixel. So you can see that the 4 pixels has been selected and their average value will be assigned as the new value in the output image. So what is the advantage? The advantage is stair step effects caused by the near neighborhood approach is reduced, and because you have done the average. So when you're done when you're performing an average technique, obviously your image will be more smooth. What will be the disadvantage? Disadvantage is alters the original image, because you are performing a average. So what it will do, it will change the value of your original data and will reduce the contrast on the image, because you are performing a average operation, and it's computationally more expensive than nearest neighborhood. So it's more costly if you're performing a bilinear interpolation and you're comparing that with a nearest neighborhood. It has got maximum pricing involved. And in the same way around, when you are going for the cubic convolution, in the cubic convolution the approaches uses the weighted average of nearest 16 pixels to the output pixel. So you can see that the 16 pixels were taken into consideration for providing the output value in the output image. So this is the same way how the bilinear interpolation is done, but because the averaging of the pixels, we have taken a larger bracket, we have taken more number of pixels. So obviously what it will do, it will provide a more smoother image, a more average image, a more difference can be in the image when you see what was there in that object. So it is more smooth, means many of the smaller features must have removed from your satellite images. That's why you are getting a smooth images. So the advantage as it was that the state step effect caused by nearest is reduced. It's smooth because we are using 16 pixels average value. So obviously it will be having a more smooth, and then you will be having a altered image. It's more expensive than nearest neighborhood and bilinear interpolation. So you can see that how when we are using nearest neighborhood, only the nearest pixel is taken into consideration to get the output value. When you are taking the bilinear interpolation, you are taking 4 pixels, the average value is determined to get the new value of the new pixels in the output image. And when we say about cubic convolution, we are taking 16 pixels, the average values are to be determined and to be fixed in the cubic convolution. So these are the few ground control points, that how you will be identifying the same ground control points that are seen on a topographical image and a satellite image, and thereafter will be rectifying that image. That same you have to identify, and thereafter you will be performing this mathematical, their entire statistics will be generated when you're performing all this exercise, and thereafter you will be getting a geo rectified image. And with this I would like to conclude my today's lecture, and I hope that I have done justice to my topic. And then after this, is there any question? We'll be doing a quiz, a round of a group discussion, and thereafter we'll conclude. Okay, then I'm stopping my recording for today's class. Thanks a lot.